All right, morning. I hope you had a chance to review the talk we have discussed last week. So today, I hope everybody had a good time after the fall break. And this is going to be one of the last few lectures on this scattering courses. So I tried to use this class to cover one of the topic Makira asked me to cover on single chain conformation. I think this is quite different to other science example I talked about, because the other few, the first two is mostly on the structure factor. I talk about packing of block polymer, packing of lattice. So today it will be slightly different on conformation of the single chain, which is mostly focusing on the form factor or how individual polymer behaves. So let's begin today's lecture. For those who are in my class, you might find this a little bit redundant because in my group we have talked about this data, most of them. But for those who haven't heard about it, will be interesting to many of you. So today, again, we're going to cover these basic questions. So when we consider a single chain conformation, it apparently will be very different with what we discussed in the past couple lectures, which is mostly on solid samples, or thin film samples. Why we have to measure single chain conformation in solution? I'm going to begin this question to everybody. So anyone can give me a hint? Not in my research group, so anyone else want to give a try? If I want to understand a single chain conformation, why not just to measure it in bulk?
You would have interparticle interactions in bulk, so you wouldn't have a true intrinsic conformation to your chain.
Very much true. So, Michael, you are certainly a master of my class well. So there's two reasons. First, when you measure in the solid states, let's assume it's amorphous polymer, it's a polystyrene sample, you're not going to have much contrast in the low Q, because at low Q what we are looking at is just a scattering signal at a larger distance. And at that length scale, we don't observe much scattering length density difference. So there's no contrast between the polystyrene chain you want to measure to the neighboring chain. They all look the same. It's very much similar to the concept that when you look at when you look at this, for example, this whiteboard, if I use a white pen to write a text, you want to see it because it's the same with the neighboring. There's no contrast, right? In order to see that what I'm writing on whiteboard, I need to use a different color other than white. Can be orange, can be black, can be anything, right? As long as you have contrast, you will be able to see it. So most of the scattering experiment for single chain are measured in solution states. With a few exceptions I will talk at the end. There's a few ways you can measure in solid states, and that's unique to some of the techniques that our speaker talked about last week. He actually is a speaker, talks quite a bit about neutron scattering. I'll use the first few minutes to fill in what's the difference between neutrons and X-ray. And I think some of you already mastered it, right? So he already mentioned the neutron and X-rays interact with our material very differently. So throughout all lecture, we talked about how the X-ray interact with our material. So which portion of your molecular or molecular atomic structure interact with your X-rays?
Electron density.
Michael, you are off the chart. Electron density. The outer shell, each atom you have a nucleus, they have electron, orbiting around it. So that's where it's primary reason how you interact with normal X-ray scattering. So the electron density is linearly increasing with atomic numbers. So the heavy elements, you have a more dense electron clouds. So that's why if you throw in some metal particles in a polymer, it will have a lot of contrast, right? So how about neutrons? It will interact very differently. So anyone would make a guess?
Neutrons don't carry a charge, so they only interact with the nucleus and not the electron cloud.
Yeah, that's right. Good job. So neutrons see things very differently. As As mentioned, it's only intact with the core part of the element. So the surrounding electron cloud doesn't interact with it. This brings two benefits. The first one is it doesn't interact with electron clouds, so it has different interaction mechanism. Okay? What I mean is scattering length density is different for neutron versus X-rays. As you see in last speaker's notes that, for example, hydrogen and deuterium is similar to the X-ray but very different to neutron. So we can do interesting chemistry. I will talk more in the later part of it. That's one way is you can take advantage of different scattering length density with respect to different elements using neutrons, okay? The second benefit is since electron clouds is orbit about nuclei, and nuclei is very tiny. So neutron is very much can hit the sample and pass majority of the sample, because if there's no nuclei, it's just going to pass it. So it has very strong penetration power. So a lot of neutrons are typically much more penetrating, and there's a few elements absorbs neutrons specifically well, but most of the case, what X-ray cannot pass, neutron can pass it. For example, we learned about attenuation length for X-ray, right? We talked about for polymer, that's about a few millimeter is ideal range. If you have a few centimeter, X-ray just cannot pass it with low energy. Low energy means the energy we typically use. So neutrons is not limited by that. It can pass a centimeter of polymers easily. It can even pass more dense materials, such as if you have a block of aluminum, it can pass it as well. If you have irons, it can pass it as well. A few inches of those metals is not a problem. So you can see it's a unique particle that is unique for its ability to penetrate the material. So a lot of neutron experiments are taking advantage of that. You can measure, for example, running engine, a car engine in the neutrons, which is otherwise impossible to do X-ray, because how you would pass this layers of metal without being absorbed. Okay, so back to the topic today. I'll chat a little bit more about the ability to change scattering length density by using deuteration. That's a very powerful technique, as we will discover more today. Okay. So with respect to solution, there's other features that pertains to our discussion. So I'll address these two. And this is especially useful for solution scattering. Scattering length density contrast form factor. This can be manipulated to achieve very interesting phenomena and measure scattering of portion of your molecule. Sample thickness, this is again true. Although we measure the polymer in solution, we shoot the X-ray past a polymer solution. The absorption is still potentially an issue because solvents absorb the X-ray as well. Okay, so instead of we need to worry about thickness of a solid sample, here we need to convert this to the solution sample. I'll chat a little bit more at the end. But generally speaking, the density, electron density for any organic non-halogenated solvent is similar to polymer sample. So this rule still applies. So a few millimeter solvents is not too challenging with a 10 kilo electron voltage of X-ray. But this number attenuation length will dramatically lowered if you have a weaker or softer lower energy X-ray, such as if you use X-ray at 200 electron volts instead of 8,000, your penetration depth will drop quite a bit. Or if your solvent is now have halogenated atoms such as chlorine, this covers examples such as benzene, dichlorobenzene. For those solvents, it has a strong ability to absorb X-ray. So a millimeter of liquids will absorb all the X-ray at about 10 keV. So you use either narrow beam pass, reduce it beam pass from a few millimeters down to a few microns. You can shoot through those chlorinated solvents, or you can use high energy X-ray. Either way, there's a way to get around. Last point, I will revisit. This is not particularly important because in solution state, it's almost guaranteed that you're going to have an isotropic sample. Just because polymer has a lot of dynamics, it can move around. So to start, I will spend a few minutes to talk about why sometimes people want to study conformation. In the field that I study is relevant to organic electronics. So we deal with polymer with conjugation along its backbone. Okay, polymer has alternating single and double bonds, and people discover that how rigid the backbone plays a role, and torsion angle and bending all affect their material's property. If this backbone is perfect straight, then it can create a very strong delocalizing effect. Your electron can move along pretty fast. But once it starts to, this is an example shows what electron clouds density looks like. It can also use computational method to simulate them. Another few examples are some of the material we played in our lab. This is called diketone pearl polymer. It has a quite complex backbone. It has a couple of 5-member selfing rings. This is a fused DPP polymer. You have typically a DP about 30 or 40. Or if you're very good at making them, you can increase this at about a DP of 100. So your polymer is talking about the length. If the pull fully straight, you have a contour length about 10 nanometer up to 100 nanometer possible, depending on degree of polymerization. The sidechains help polymer to be solubilized. So example is shown here, where if we put these sidechains in the backbone, this is what it roughly looks like. There's not necessary to be, there is pipeline for the DPP and pipeline for the other plane. They are not necessary to be planar, and they could even bend. So this is a great example of how we can use scattering to extract the form factor. Okay? Form factor is what we mean by looking at how a single chain looks like in solution states. Some of the kind of the motivation for us to look is some simulation people already predicted. This is one kind of conformation for this molecular. You have the sidechain coming off. This is backbone. And this looks like fairly straight, and usually this is classified as raw light polymer. So very rigid. And if there's a lot of bending and torsion along the backbone, you can see the backbone needs to wind back and forth. Whenever there's a strong bending effect, you lose conjugation in our science example, and you would have a shorter conjugation length and weaker electronic property. So in our science example, it's kind of quite clear. We want to see how rigid these polymers are, right? That's a good example. We can measure the rigidity of these material and confirms molecular design rule how to make very rigid example. So some theoretical example called Trossi from UK. he actually wrote a theoretical paper. They are a computational group. They basically apply a few constraints in their simulation model. See, if there's bending above a certain angle, you're going to break the conjugation. Then it's going to slow down for the electrons to travel along this way. So they basically predict if you have a very strong, long persistence lens, we have a better diffusion coefficient in electrons, or which means we have a better charge transport property. So it's great. There's some theory is predicting or helping you to understand your sample, but how exactly we can measure chain conformation? It's not too hard, as we explained to everybody. We just need to disperse these samples in solution and understanding their chain conformation. Okay? Right? But it's actually pretty hard in our science case, just because if it's a linear alkyl chain along the backbone, this experiment will be much easier. You can easily find a solvents such as THF or toluene to dissolve. For example, this is polyethylene. You can dissolve them at the relatively low concentration, a few percent to 1%. Then you can run small angle X-ray scattering. Then you will address this problem. And this is actually routinely done. There's a lot of X-ray beamline is dedicated to either small molecular or macromolecular related to biological research. So in material science, I think it's not a lot of great use, but in biology, people constantly trying to search and answer if this protein is being denatured, how this would impact its activity in your body, or how this would be translated to a certain disease. So let's say in a synchrotron, that where I used to go a lot in ALS, they have several biology beamline dedicated to do solution scattering in biosamples, biomolecular specifically. And what they do is typically very standard. They will discover a biomolecular. It will be dispersed in water or physiological conditions, a biopolymer with some salt buffer, okay? Then they could directly use X-ray to measure them. In polymer, in the early days, there's a lot of work to look at persistence lens for conventional polymer, such as polystyrene, PE, etc., etc. Again, those going to be dissolved in toluene, THF, and you typically can run X-ray fairly straightforward. But in our lab, we have two challenges. What are these two? First is, if you throw this in toluene, Michael will tell you likely they're not going to dissolve well. Even they could dissolve, it's only a small fraction of it's being dissolved. Usually less than maybe 1%. Majority is still solid, dispersed at bottom. If the concentration is low, it's not mean you cannot do scattering, but you need to do it really carefully. You need to consider the background signal coming from cosmetic ray, the readout detector. So typically, the signal will be too weak and too noisy to do meaningful analysis. So we resort to chlorinated solvents, which is chlorobenzene or dichlorobenzene. And I already mentioned to everybody, there's one limitation. Limitation one is you cannot use 8K EV X-ray to run it using a millimeter thick typical cell to run it. Just it will absorb most of the X-ray signal. There are several ways to go around that. You could go to a beamline that runs 20 keV, will address the absorption issue, and there are several beamlines is possible to run at their high energy. Notably in new synchrotrons such as NSLS2 in Brookhaven National Lab or in APS in Argonne National Lab. Those are possible, okay? But it's typically takes longer time. The other way is you need to design some special cell to shrink how thick your samples are. Go from a typical where we use a capillary tube. I don't think I have an example here, but whenever you guys go to the lab, I'll show you what the capillary tube looks like. And these are typically on the millimeter. And you need to design your own cells and reduce the thickness of the solution down to, let's say, 20 microns to 100 microns. Then you can do similar experiment. This is problem one, absorption of chlorinated solvent. And if you do scattering lens density, it might be beneficial to you. A side effect of you putting a lot of chlorinated solvent is the solvent scattering lens density or the contrast with your polymer will be very high, because you can think about your solvent is scattered very strongly, or SLD is big. Okay. The second challenge is our polymer like to aggregate each other. Okay. So there's a lot of pi interaction. So this molecule at room temperature, it has a tendency to collapse with another molecule, form a dimer or trimer, or in some extreme cases, it will aggregate into a nanofiber. So in this scenario, if you run scattering, you likely reach the wrong conclusion because you're not measuring a single chain anymore. That's the second caveat that you need to address in our science case. And we have other secondary techniques to confirm we don't have lots of aggregation. Because once it's aggregated, your optical signal will be different. But there's a lot of literature shows if you have a high rigidity, for example, in this paper presented by Nielsen Group says, if you have a persistence lens, as we know, a quantification of rigidity with respect to different polymers, some of the polymer is very high, up to 425 angstroms, some of them are low. If you can design some polymer is really high, then you can get what the value for this is. Extinguishing coefficient will be increased, and likely the absorption will be redshifted because of delocalization effect. So that's inspired us to look at what is conformation. Additionally, there's so many materials people are using in organic electronics. So if you talk to Michael, he will tell you probably this is only part of molecular Jason asked him to combine and make new molecule, right? They have a library of different donor and acceptor. They each can be combined and coupled to create new molecules. So if you pick one on this large library, the other, this already creates hundreds of molecules. But out of the wild, you get almost hundreds of thousands of different acceptors you can pick. So the combination is almost unlimited. That ask is, how can we not use the try and error method? Let's say, pick two molecules, try them and see how they work out. Instead of go the other way, we use some calculation and modeling to predict what is donor and acceptor we want to use, which tend to be less costly to make and more efficient to make this. So that requires us to predict the conformation and the rigidity. So coming back here, to get the rigidity, LP is a preferred parameter. If everybody still remember my polymer physics class for 3-4 years back, LP stands for persistence length. That's the length roughly, the layman's terms says it takes how long for the chain to bend 90 degrees. So you can use that to understand how long the persistence length. A garden hose has the persistence length on those semi-rigid one, you think about a feet or two is roughly the persistence length of the garden hose, okay? If you have something really flexible, such as, let me think about a science example. A fishing line, maybe, that will certainly have a much smaller persistence length. But here we need to measure what is LP. And there's a couple techniques we could use to probe this LP using small angle scattering technique. There's already a couple people doing this. This is an example done by Rachel Siegerman group in macromolecular back in 2013, almost 10 years ago, What they did is, they're trying to understand when there is different sidechain group attached to the polysulfane, how rigid these polysulfanes will be. In this case, the backbone is the same, but what they are changing is different sidechains, and they can use scattering to measure it. Let me show you a little bit how experimental-wise they do. You would take a few milligrams of polymer, you dissolve them in a vial, and you would add in good solvents. Typically, in this case, they are using chlorobenzene. You stir and heat them overnight to ensure they all goes into the solution. Commonly, people do a quick filtering before you load it into the sample cell. Okay? Then you can measure scattering. In this case, they actually did a neutron scattering. And this is what you would get. Still remember, intensity versus the Q plot. You can control the STD to get different Q. In this, because they use neutrons, okay, so it's slightly different. But fundamentally, they go to a neutron beam line and load the sample in the neutron beams, and neutron hit the sample. And you collect the signal using a neutron detector. Fundamentally, no difference. And the data analysis, no difference as well. In this case, they could measure what's the conformation and rigidity. And so here, this is, remember, this is Guinea region. You absolutely need to reach at least a portion of Guinea region to get a reliable fit. Otherwise, if we don't measure, let's say we chop away this Q range, all you have is slope. Then you likely will have some trouble because the unmeasured data could continue and go here. That will give you totally different values when you fit the model. So it's absolutely important you pick your right STD to cover the proper Q range. If you want to measure the conformation, you need to get the low Q ranges to measure the scattering signal, okay? High Q is also important. So if we remember for the polymer, it will have several models. There's the bi model. If everybody still remember, in my lecture notebook, this is an ideal Gaussian chain. It will follow the bi model. It will go down, then roughly plateau. Okay, so they haven't reached a high enough Q to measure the high Q region. Ideally, you want to cover enough Q to cover both Guinea region and high Q region, or this is already polar region, so high Q region is going to be here, and it will be good to cover. Well, we saw the result. What they observe is when you increase the sidechain length, the persistence length would drop, indicating that your steering hinges from sidechain will distort your polymer backbone, make it more wavy. Okay, you can use solution scattering to look at such experiment. Very easy, right? In our case, we did something different. It was very good inspiration for us to think about how we can use neutrons. But one of the experiments we are trying to understand is how does this sidechain impact the backbone conformation. So let me emphasize one more thing. In here, in this example, it didn't show what the sidechain in this cartoon or this red schematics, but when neutron measures, it measures everything. The contrast comes from your polymer backbone, the sidechain versus solvents. Okay? Let me repeat it one more time. What you're measuring is the selfing and the backbone. They both scatters neutrons or X-rays, depending on what techniques you use. But in our science case, we know that the backbone is most interesting because this is electronic active. The sidechain is put there to make it soluble. So we ask the science question, is it possible to measure just the backbone conformation without sidechain? Some of you might think if we chop away the sidechain, then we measure it. But it's not that simple, actually. When you don't have the sidechain, the polymer is not soluble. It's behave like maybe some orange blackish powder, but it doesn't dissolve in any chlorinated solvent, no matter how high you heat them. So the other way we can think about is actually hide the sidechains. And there are several unique things we can do with neutron scattering. For example, in neutron community, they already developed something called contrast mesh scattering. What does contrast mesh scattering means? So let's look at here. First, let's look at what we're trying to show. This is actually the example of a protein which has, for example, if your part of protein is being deuterated, which means you replace hydrogen with deuterium. So let's assume the black part is deuterated, okay? So what does deuteration do? At the beginning of the lecture, I mentioned deuterium replace a hydrogen can help you change the scattering length density. So this is a schematic shows if I replace those hydrogen on the portion of the polymer that I'm interested, I can change the contrast. This will show as black color roughly indicates it scatters neutrons more readily. And the other part, if I don't deuterate it, I just make it normal ability to scatter a neutron. So you can think about if you are making a diblock polymer, this will be block A, non-deuterate, block B, deuterate, okay? And if you throw in the solution, part of the chain will look like lighter color, the other looks darker color. So saying now that what does neutron can do is neutron can throw in different combination of solvent. You not only can deuterate the polymer, you can deuterate solvents. And you don't need to do deuteration because solvent molecular is typically very tiny, right? If you think about a water molecular, hydrogen oxygen bond is on the order of about 2 angstroms. So the molecular is typically just a few angstroms for solvents. So in the low Q scattering region, if you mix 2 solvents, it cannot tell there's 2 solvents there. It looks just one uniform solvent to it with an average scattering length density. Okay? So that's what the beauty of the contrast matching is. Now we can throw different solvents in it. And solvents is not, I mean, you mix in toluene and hexane. You just mix in the same. In this case, we mix in the water, but we are mixing H2O with D2O. D2O is deuterate version of H2O, okay? So D2O has much scattering length density. D2O is much higher at scattering length density about 6. H2O is minus 0.5. So by mixing, let's say 10:9 ratio with a 5:5, you can change the different scattering length density for solvent. Either way to think about is you have a black ink, you have a white ink. By mixing different ratio, you can have a different gray scale for the solvent. Right? You can make it very dark if you're putting a lot of dark ink, or if you pay majority light ink, you can change it. And your solvents, your polymer now can be put into the solvent to create scattering. And depending on the background color of this solvent, you can create different contrast. So that's what this shows. If I mix 42% of a D2O, heavy water, into the light water, I can make the solvent scatter as strong as this part of molecular. Okay? So that's why in this schematic, the solvents, which shows this big gray background, which looks like very much similar to the left part of molecular, it can conceal, it can do a camouflage for this part of molecular. So although it's still attached to this giant macromolecular, but it no longer scatters. What you measure is only scattering from this black part. It's kind of quite neat, right? You can do scattering, but without part of molecular. If you only want to see what happens to this part of molecular, you can do that. Similarly, you can change the contrast of solvent, make it scatter much stronger. Blending in more D2O, which means scattering length density will increase for the solvent. At some point, it will match the other part of molecular. Now this is look like black ink, and your light gray will stand out in this. And you can measure the other part of molecular. Okay? So this is a good example, shows you some ability that unique to neutrons is you can control scattering density through contrast matching experiment. Okay? So if I'm wearing two color, I can do contrast measure experiment as well. If I stay in a very dark room, my shirt's gonna pops out. You're gonna see the top part. If I stay in a light room, my pants gonna pops out, right? You will see this is more dominantly. And that's what people do. I'll show you a few examples. This is again P3HT. As I tell you, the hypothesis is what we want to measure just the backbone part. Without deuteration, you can calculate what's the scattering length density using the equation we showed before. So the backbone, do scatter a little bit stronger than the sidechain. This is mostly composed of carbon and hydrogen. That's a SLD for the sidechain. There's some contrast. You can already do contrast matching, but it's not as strong as we want. If they have even bigger differences, it will be much easier to run because then the other part will diffract much stronger. So let's replace all these hydrogen on the sidechain, all these gray ones to this blue one. Blue one is deuterating. Its band neutrons much stronger. If we calculate contrast, this goes now up to 7.7. Now if you put in ink that matches 7.7, then you can do scattering only the backbone. You can look at the backbone conformation. Okay? Any questions so far? Okay, if not, let's continue. Some data, what we collect from detector. And this is a calculate what's the scattering length density, or SLD. You can get it if you know the molecular structure, the density, and what elements there. So if we look at what this plot is SLD for different part of molecular. This says the scattering from, that's a backbone, and this green one is the sidechain, right? As we show, we already calculated. And on the bottom, we can mix chlorobenzene deuterated versus non-deuterated. If we put everything as non-deuterated chlorobenzene, we have SLD, matches the backbone pretty well. If we put in 100% deuterated, we have SLD here. You can see we didn't reach the ideal state that matches everything about sidechain, then you can do the backbone. That's some of the limitation. Okay, because the solvent only scatters this strong unless you do something to the solvent. But by combining different scattering region in here, here, you can deconvolute contribution from sidechain and backbone. I won't go into details, but here you can see different contrast matching conditions. The other work you can look at, now we're going to switch the gear. The other work you can look at is look at different sidechains information, impact on conformation. So in this case, we can look at DPP polymers with different sidechains and understand how they will scatter. And 1D image really don't tell you much, but you can model this with either use the SAS view software to model how rigid these polymers are. It can be reflected by this cone length value, okay? And cone length will tell you how rigid these molecules are. Some of the other example we did was with Dr. May on conjugation breaker molecular. So most of the conjugated polymers are fully conjugated and they're relatively rigid. Some of the unique experiment that Dr. May did was putting on alkyl chains. This will make this portion of the molecule very flexible. And we kind of expected we will have a huge drop in persistence length. because these are soft flexible segments. And as we measured it, we see quite a strong drops in persistence length as well. So this is the data. Again, we dissolve the polymer in coral benzene, go to a neutron beam line, put them in the neutron beams, measure them, and convert 2D data to 1D data, okay, in the SAS view software. And we can look at Coulomb length has a quite dramatic drop. For fully conjugated, it's about 20 nanometer. For non-conjugated, it goes from 8 nanometer all the way to 4.5 nanometer, so quite flexible. There's a couple impact we found. Rigidity also impact crystallization. I won't go into too much detail, but here is an example when crystallization depends on rigidity. When the polymer is, here is the example, when polymer has, this is one with crystallization temperature, Tc minus T0. So when this is more rigid, you have a tendency to have increased crystallization rate, okay? So rigidity, certainly we found could be tied into crystallization kinetics. And last part, I want to discuss this work. This is a very classical work that has been later found. It's called confinement in solid states. Up to now, I only talked about polymer in solution state to look at chain conformation. So you can measure anything dissolved in solvents, because in this case, we can measure isolated chain, and we can measure form factor for individual molecular. But is it possible to measure conformation in solid states? When Michael said at the beginning there is no contrast, that's totally true. But there is a trick we can do if you're doing neutron scattering, okay? In X-ray, it's impossible, because it's very hard to change the scattering length density without changing the molecular. The only way you can change that is, for example, you replace a carbon with a heteroatom with silicon, but that comes into consequence that your molecular property likely going to be altered, right? But in neutrons, it's possible to replace a hydrogen with deuterium. They're similar in size, so a lot of time your material's property is maintained. Polystyrene, deuterated polystyrene, still behave like polystyrene. Okay, so we have a way to change scattering length density, but to maintain its material's property allows us to do something cool. For example, here you could measure now solid state chain conformation. How do we do that? Is we could blend a couple of these deuterated polystyrene in a matrix of hydrogenated polystyrene. Okay, now you have contrast, right? The contrast comes from deuterium and hydrogen. And in this scenario, the hydrogenated polystyrene actually behaves just like a solvent. It disperses those few percentage of deuterated polystyrene in it. Then you can do scattering and measure the conformation of those deuterated polystyrene. That's how you measure solid states conformation. Historically, it's played a big role. So let me tell you some interesting fact about polymer physics. So in the early days, we know when we started about polymer physics class, what we first talk about is Gaussian coil or random walk. And if everybody remember, random walk only happens in two special conditions. One is in Theta solvents. When the quality solvent is not so good, but not either bad solvent, you could achieve a state that behave like idealized chain. The second condition is in melt. And this was predicted before anyone could measure it. So Paul Flory was mentioned that in melt states, you could observe the polymer would adopt idealized chain conformation, but nobody could have any ability to measure it by then. He predicted in the 50s, late 50s, early 60s, but by then, There's no way, there's no good microscope can measure a single chain conformation. Neither, nobody could do neutron scattering at that point. Neutron scattering was just at the beginning. It started in the late 50s, so it haven't reached a stage can be used for research in polymer. But later on in the 80s, that's actually how people discover what Paul Flory said was totally true. Because people couldn't make now deuterated polystyrene. And the first major contribution neutron did in the community is to confirm what Paul Flory has suggested. Your chain conformation is a Gaussian coil. There's no swelling in a polymer chain in the good solvent, for example, observed in the metal states. And the experiment is very simple. You just load a few percent, for example, 5% deuterated polystyrene, mixed in hydrogenated polystyrene, heat up them to the melt, let them equilibrate. Then you put into neutrons to measure it. Then you can measure single chain conformation. And you can measure conformation dependence on the molecular weight so that you can extrapolate what is the dependence of Rg on molecular weight. And he observed that it's scaled with molecular weight of around 0.5. So it's idealized chain. Okay? So it was quite nice because back in the 70s and 80s, way before I was born, that was a major contribution to the community. And after that, there's a couple here and there to look at melt state conformation, but not a lot. Just the challenge is the scattering is, the deuterated material are generally very expensive to make, so it's very costly to perform something like a solid state conformation. You require several grams of polymer, and this could be costly if you don't have already those material made, okay? But still, this is a possibility if you want to measure solid state single chain conformation. You can use this technique. As long as you can convince your advisor to provide those material to you. Okay, so what about this paper? This paper was published in late 90s. And this is an example they show how does conformation depend on this film thickness. So apart from the Gaussian coil, there's another group led by Sunal Kumar, Ronald Jones, and my previous PhD advisor, Tom Russell. What they're looking at is if we reduce the film thickness, how does polymer coil conformation changes? So when it's confined, will your Gaussian coil like squeeze a donut, it will expand in one direction and once you squeeze. Okay, or like a balloon, if you squeeze in one direction, it will likely will expand. And they said, okay, let's throw a few 100 nanometer film on a substrate. So in this case, you can just spin coat a polymer in a substrate on the order of tens of nanometer. And silicon substrate is almost transparent to neutrons. Although it's silicon, but neutrons don't see it. It's transparent. So you can stack layers of films. 100 nanometer film is very weak for neutron to do transmission. So you need to stack it like 50 wafers on the top of each other. Then you can have accumulate enough scattering volume from your polymer to run it. And what they found is here, this is a Karaki plot for confined and confined state. There's no differences they see. So they concluded that even you squeeze the polymer, it is not going to expand. So think about now you squeeze a balloon. The harder you squeeze, it just shrink in this direction, but don't have anything to do in the other direction. Well, this is only a few examples. You can actually measure it. There's other debates along this line, but I won't go into detail, but let you know this is possible to measure in solid states, okay? So coming back to the overview, if you want to measure single chain, you need to make sure you're doing this. Use SEX, small angle X-ray, not in the wide angle region, because you're likely going to miss the Ganier. So use small angle X-ray or neutrons to look at the form factor. Okay? Typically, it's down in solution states. And you don't want to get into trouble in null states. I would strongly recommend start with solution states. Pick a good solution. You can disperse your film very well. The measurement actually is a little bit complex. You need to measure polymer in solution, and you need to measure the solvents only. Because solvents create a background, you need to subtract the solvent background so that you can get the polymer scattering only. Okay? So I don't think I have seen proposals want to do that in here. But if you're interested to that, happy to chat with you individually how experimentally you can run this. Okay? The other important factor I already covered, that the Q range needs to match with the size of interest. So if you're measuring the RG of a small molecular, let's say, expect the RG of tens of nanometer, your Q at least need to reach 1 divided by that RG. Ideally, even smaller, right? So if you have the setup we have there, it could measure RG up to about 100 nanometer, but anything bigger than RG 100 nanometer will be harder to measure using our instrument upstairs. You need to consider scattering contrast. This typically is not too bad, but when you pick a good solvent can disperse your polymer, do a quick out of envelope to understand SLD, scattering length density of your polymer. Make sure your solvent is different. Let's say polystyrene, use this example. If I could dissolve polystyrene in toluene or THF, I will likely do it in THF. Why? Because if you think about toluene, it will have similar SLD compared to polystyrene, given that the chemical structure is quite similar. Or THF would be able to dissolve equally well. I would do in that solvent. Okay? SLD can be calculated either directly or use the NIST website or in the ALS website, right? I shared everybody. You should be able to look at SLD. Okay, this is important. Is my sample too thick? The transmission is, again, needs to be considered. Solvents cannot be too thick. Okay, X-ray cannot shoot through very thick layer. 1 millimeter is typical for non-halogenated polymer. For example, using the example I talked about, if you use, let's say, something like some of you measure in the cuvette in UV vis, these are on the order of 5 millimeter. If you throw in the X-ray, you're not going to see anything because everything is being absorbed. Okay? So 1 millimeter is ideal. If too thin, you also have the signal issue. You want to choose roughly about 1 millimeter. Isotropic is straightforward. We don't need to cover that. So this wraps up today's lecture on chain conformation for a single chain in solution. Any question for me? No? All right, folks, then we can finish today's lecture. So in this Thursday, we're going to meet. Then I'll make a few assignments. I looked at the calendar. We have 3 weeks until the Thanksgiving. So there's no class on Thanksgiving week. So before that, we have 3 weeks. So we can accommodate 6 mini group. Looks like I should be able to just mix match about 2 to 3, a small group, interested in the same technique. Then you can go ahead and prepare a couple sample and try to run it. So I'll work with my student. It's likely going to either Gurung or Luke, who are senior and knows tools well, take turns to lead some of the efforts in that. We're going to cover a few topics. So what I'm going to suggest is we're going to reserve the 2 for half of the day. That's typically good for measure quite a few samples. One single sample measurement time is on the order of tens of minutes to maybe up to an hour. So half day should be planned to measure everybody's sample. So you should, when I'll announce the schedule, then if it's your schedule, let's meet together on the time to go through the sample measurement. Otherwise, I don't think you need to be in the device lab or X-ray labs to look it over if it may be getting crowded there. Okay? So any question for me for that? If not, then let's meet again Thursday. We're going to go through how we arrange the measurement and how we're going to set up differently so that we can know what the schedule. I know some of you email me in restriction in your travel time. If you have a few weeks you cannot be here, please let me know by tomorrow evening. Then I'll try to arrange that so the schedule would work out with everybody. Okay? If no more questions, let's finish today. Thanks.